Okay, so last time I introduced the algebra of quaternions. Let me review quickly. Yeah, people should mute themselves and should stop talking about other things. Please focus. Yeah. So let me review what we did quickly last time. So we understood this result of Euler at least one way, that an orthogonal 3 by 3 matrix of determinant 1, that means a matrix is in SO3. Then if you take linear transformation induced by that from R3 to R3, that is a rotation. And then I also discussed finite subgroups of orthogonal group O2 and the special orthogonal SO2. And I introduced the quaternions. And of course, we did the computation of composition of two Householder matrices. So I take one Householder matrix, which is matrix of reflection with respect to a plane which is perpendicular to U, and then take another similar Householder matrix of reflection with respect to a plane which is perpendicular to V. So when I multiply these two matrices, it is a orthogonal matrix of determinant 1. And we were trying to show that it's a rotation matrix. It's a matrix of rotation. And we identified the axis of rotation. The axis of rotation is parallel to U cross V. And the plane of rotation is the plane of U and V. So U and V, if A is not an identity matrix, U and V are not parallel, and they constitute a plane. And the plane which is span of U and V is the plane of rotation of HU, HV, 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 HU, and the axis of rotation is U cross V. It is in the direction of U cross V. And this we did by simple calculation. We just applied HU and HV on U and V and found out the angle of rotation. The angle of rotation of HU, HV turned out to be 2 theta, right? This turned out to be 2 theta. So we found the matrix of this transformation from R2 to R2. So take this plane which is spanned by U and V, and the linear transformation which is induced by this matrix A in SO3 is also mapping vectors from LUV to LUV. So this was clear from this computation that we did. HU, HV is mapping U and V to linear combinations of, so U was mapped to this vector, which is a linear combination of U and V. And V was also mapped to this vector, which is a linear combination of U and V. And U and V, they are linearly independent. So then we found the matrix of this linear transformation with respect to U and V, and then computed the angle of rotation. And then I discussed the finite subgroups of O2 and SO2. Yeah. And the trick there was that first understand the finite subgroups of SO2. So take this finite subgroup of O2, intersect with SO2, that is a finite subgroup of SO2. And then we said that, okay, it has finitely many rotations. So look at those angles of rotations, take the minimum of those two angles and the rotation with respect to this minimum angle. This generates that subgroup of SO2. So if it is generated by this rotation by angle theta, then that is the characterization of finite subgroup SO2. And if I have a subgroup of O2 which is not really contained in SO2, then there is a matrix in H which is not in SO2. So its determinant is -1. 2 by 2 orthogonal matrix of determinant -1 is a reflection. And then we showed that if you pick this reflection, then the whole group H, which is a finite subgroup O2, is a disjoint union of two right cosets of its intersection with SO2, and then that says that the group is the dihedral group, okay, of order 2n. Yeah, so this is what we did last time. And then I introduced the quaternion algebra. The quaternion algebra it puts a multiplicative structure on the four-dimensional space. Yeah, so take yeah, so right, yeah, so R4. So take a basis of R4. Okay, R4 has a basis, and call it as 1, I, J, and K. And then every member of R4 is a vector with 4 components. So write it this way. Yeah. And then we define the conjugate of this quaternion, just like we define conjugate of complex numbers. So it is A minus BI minus EJ minus DK. And IJK are, we are putting a multiplicative structure on this vector space. So, and since all quaternions are real linear combinations of 1, I, J, and K, it is enough to know how to multiply I, J, K with among themselves. And there, these rules of multiplication are that I square equal to J square equal to K square equal to IJK equal to -1. So this is part of the axioms of this algebra of quaternions. And this is not artificial. It can be achieved by working inside 2 by 2 complex matrices. Yeah. So then using the conjugate, we saw that Q times Q bar. Okay, you can multiply Q and Q bar using the rules for multiplication of IJK, and that is A square plus B square plus C square plus D square. So if Q is not equal to 0, then this is not equal to 0. Okay, and so if you divide Q bar by this real number, yeah, then Q times this is equal to 1, and therefore this is the inverse of this quaternion. So non-zero quaternions have inverse, but it is not a commutative ring, because I times J is not J times I. Otherwise, it is a field. Only the commutativity is violated in algebra of quaternion. So we say the quaternions form a skew field. Yeah, this terminology used sometime, that quaternions form a skew field. That is when multiplication is not commutative, but all other axioms of a field are satisfied. Yeah. So then I introduced this homomorphism from the algebra of quaternion to the ring of 2 by 2 matrices. So algebra of quaternion is a ring. Yeah, under addition it is, and scalar multiplication, it's a 4-dimensional real vector space. But we have introduced multiplication, so it becomes a non-commutative ring. And we define a homomorphism mapping a quaternion Q, A plus BI plus EJ plus DK, to this matrix, where the first entry is A plus IB, the second entry is C plus ID, and then this is equal to negative of the conjugate of this, and this is the conjugate of A plus IB. Okay, yeah. So you can check that every matrix in SU2 looks like this. I mean, every matrix in U2 looks like this, because A star is inverse of A. So you can write A star, you can write inverse of A. Yeah. If A square plus B square plus C square plus D square is not equal to 0, then this matrix will have inverse. Its determinant is A square plus B square plus C square plus D square. Yeah. So non-zero quaternions go to invertible matrices. And this, since the determinant of product is product of determinants, this map phi is a ring homomorphism. Yeah, it preserves addition and multiplication. And so this phi is also injective map. Yeah, 2 distinct quaternions go to 2 distinct matrices under this correspondence. So it's an injective map. And then you write these matrices of this type, okay, as a linear combination of these 4 matrices. So this matrix, yeah, I can write it as a linear combination of these 4 matrices. And all these 4 matrices they are members of SU2. You can check each one of these. This is identity matrix, and this matrix determinant is 1. This matrix also determinant is 1. Matrix of this K matrix has determinant 1, and these are orthogonal matrices. So every matrix which comes from this quaternion, and this is a non-zero quaternion, that becomes a linear combination of these 4 matrices in SU2. Yeah, and every matrix in SU2 comes from such a quaternion which is non-zero. So the algebra of quaternions is isomorphic to the algebra of such matrices. Okay. Yeah. So now I want to proceed further, and I want to show you a picture which I want to explain in this lecture and the lecture on Saturday. Okay. Yeah. So my purpose in introducing quaternions, quaternions are used for lots of things in geometry and in physics. And the discoverer was William Hamilton, and these are named after in his honor. Hamilton introduced quaternions to put some mathematical foundation of a branch of mechanics called Hamiltonian mechanics, and these are extensively used in physics. So here my purpose is to introduce rotations of 3-dimensional space using quaternions. Yeah, rather than so far you have understood that rotations of 3-dimensional space are linear transformation which are induced by matrices in SO3. The computation with matrices can be clumsy. Okay, so suppose you want to find out the axis of rotation. If you are given a matrix in SO3 and you know that it is representing a rotation of 3-dimensional space, so you want to find the axis of rotation, angle of rotation, plane of rotation. To find the axis of rotation, one has to find eigenvector of this matrix with eigenvalue 1. Okay. Now this we want to avoid these such computations, and you will see that using quaternions gives us a faster method to construct rotations that we desire. Okay. So I want to explain various components of this picture and then start working towards them. So the space we are working on, okay, that is this 4-dimensional space. Okay. And this 4-dimensional vector space is now being given a structure of a ring using multiplication of ijk. So rather than writing members of R4 as 4 tuples of real numbers, we are writing them as A plus BI plus CJ plus DK. Okay, where IJK, yeah, you can think of IJK as those 2x2 matrices which I wrote, or IJK are just some basis, part of a basis, and we multiply these elements using the rules of multiplication of IJ and K. Okay, all right. Now inside R4, look at quaternions of unit length. Okay, so if you look at quaternions of unit length, then these correspond to points A, B, C, D. Okay, so that A square plus B square plus C square plus D square is 1, but that is an equation of a sphere in 4-dimensional space, and that is a 3-dimensional sphere. Yeah, that is a 3-dimensional sphere. Sphere equation is A square plus B square plus C square plus D square equal to 1. So points inside this 4-dimensional space, which correspond to quaternions of unit length, they form this 3-dimensional sphere. Yeah, and so if I take such a vector in S3 and take the corresponding matrix, that matrix turns out to be inside SU2. This matrix is in SU2 because determinant of this matrix is A square plus B square plus C square plus D square, but that is equal to 1, and so its determinant is 1. But the way I have made these entries, you can check that this is This is a unitary matrix. This is a 2 by 2 unitary matrix of determinant 1. So it's a member of SU2. And every member of SU2 can be written like this. Yeah. So that is a small computational exercise for you. Every member of SU2 can be written like this. And then once you have this 2 by 2 matrix, then I look at this complex number and look at this complex number. And then to this matrix, I associate this vector. And this is a vector on the 3-dimensional sphere. So I have one-to-one correspondence between matrices in SU2 and the points on 3-dimensional sphere. And you can check that this map, which sends ABCD to this matrix, is an isomorphism. Yeah, it is clearly injective map, it is surjective map. So you have to just check that it respects multiplication. Yeah. So on one side, we have multiplication of quaternions. On another side, we have multiplication of matrices. SU2 is a group under product of matrices, but S3 is a group under multiplication of quaternions. But this correspondence that I'm indicating, that is a group isomorphism. So this SU2 and S3, they are isomorphic. Yeah. So 3-dimensional sphere is a group. 1-dimensional sphere is also a group. That is a group of rotations of the plane. 1-dimensional sphere, yeah, it's a group of rotations of the plane. And this 3-dimensional sphere is SU2. So once you have this isomorphism, you might wonder, okay, what on this right, on SU2 side, I have group theoretic data. Yeah, SU2 has its conjugacy classes, it has its subgroups. On SU3, I have some curves, right? If you have a 3-dimensional sphere, you can think of latitudes and longitudes. Latitudes are these spheres, which are obtained by cutting the 3-dimensional sphere with a plane. Okay, so intersect this 3-dimensional sphere with planes which are parallel to the equator of this 3-dimensional sphere. Okay, this is the equator of this 3-dimensional sphere. Yeah, where a equal to 0. The points on this boundary on the 3-dimensional sphere correspond to the quaternions where this a coordinate is 0. Okay.
Should we ask, sir?
Yeah, I lost
questions too.
I lost connection. Let me connect again. Can you see the screen?
Yeah, screen is visible.
Okay, so maybe my laptop got disconnected. Just a minute. Yeah, somehow I'm not able to connect. Just a minute.
What happened, sir? Your stylus is not working.
No. So I can see, I open laptop as well as iPad, but my laptop has stopped showing me anything. Somebody has to admit me or something.
So समझिए आंसर आज तो सेशन में तो नहीं सर.
Yeah, but my laptop
but
is
both the screens are visible, so
yeah,
maybe your laptop is also connected because already you are in the meeting. with the two devices.
Yeah, but somehow it has disappeared from my laptop. So that's the, I don't know how to get back to it. Just a minute.
No problem.
Anyway, the screen is visible.
Yes, sir.
Yes, sir.
Yeah.
Both the screens are visible. Sir.
Okay. All right. So I was explaining that the quaternions of unit length, they form this three-dimensional sphere, and this three-dimensional sphere and SU2, they are isomorphic. And the isomorphism is given by, take this 4 tuple of real numbers. Think of that as this quaternion. So each quaternion is sitting on this three-dimensional sphere if it has unit length, and map this to this 2 by 2 matrix. And that 2 by 2 matrix is a member of SU2, and this is an group isomorphism. Okay, so that is one side of the picture. The other side of the picture is that inside H, I look at purely imaginary quaternions where real part is 0. This A is called the real part, and these are imaginary parts. Okay, so take a quaternion which is purely imaginary. That means A is 0. So these quaternions are all real linear combination of I, J, and K. And since I, J, K are linearly independent, this is part of basis of R4. This V is a three-dimensional vector space. This V is a three-dimensional vector space. Okay, and the so the convention about quaternions is that when we look at this quaternion ABCD, this point ABCD, yeah, then the vertical axis is for the first coordinate A. Okay, yeah, so the vertical axis is for the first coordinate, that is the A axis. And this okay, so when I take BI plus CJ plus DK, that is the three-dimensional space inside the algebra of quaternions. These are called imaginary quaternions. Okay, and we will study these two structures on three-dimensional space. Just like if you look at the picture of Earth or a sphere, two-dimensional sphere, there are latitudes and longitudes. The same concepts exist in three-dimensional sphere or n-dimensional sphere. So a latitude is simply obtained by intersecting the three-dimensional sphere with a plane. Okay, this plane is defined. This plane is defined by setting x0. Suppose the coordinates are, I write coordinates of arbitrary point as x0, x1, x2, x3. Okay, in R4, this is how we write the coordinates. And x0 axis is the vertical axis. Okay, so take the plane which is having this equation, x0 equal to c. So it is at height c from the equator. The equator is obtained when I put x0 equal to 0. Okay, so on this three-dimensional sphere, the points satisfy, there are unit quaternions, right? These points on the three-dimensional sphere, they are unit quaternions. So if x0 equal to 0, then the condition is x1 square plus x2 square plus x3 square equal to 1. And that is an equation of a two-dimensional sphere in three-dimensional space. Okay, so the equator of three-dimensional sphere is a two-dimensional sphere. And then when I intersect this three-dimensional sphere with this plane x0 equal to c, yeah, look at all the points where x0 equal to c, so they are at a constant height from the equator. These form this plane. This is, I mean, this looks like a plane, but it is actually a two-dimensional sphere. Okay, and so if x0 equal to c, then the equation would become 1 minus c square. Okay, so this is, so every these structures which are obtained by intersecting the three-dimensional sphere with a plane, hyperplane, x0 equal to c is a hyperplane in R4. So if you intersect this hyperplane with three-dimensional sphere, then I get a two-dimensional sphere. Yeah. So as you vary c from 0 to 1, I get all these two-dimensional sphere which are looking like latitudes. Okay. Then the analog of longitude, they are unit circles. Longitudes are unit circles on S2, and on S3 also we will define longitudes. What I will prove next time and work towards those things today is that these latitudes and longitudes, they have group theoretic interpretation. It will turn out that the one of the longitudes, okay, one of the longitudes on this three-dimensional sphere is the group of all diagonal matrices in SU2. Diagonal matrices form a subgroup, and that subgroup, if you take all the diagonal matrices in SU2 and then use this correspondence, yeah, from SU2, I have a method of shifting to S3. So if you take all the subgroup of diagonal matrices and take the corresponding coordinates in S3, then they will be lying on one of these latitudes. I mean longitudes. There are infinitely many longitudes. Yeah. So these longitudes, we will see that every longitude is a conjugate of the group of diagonal matrices. The group of diagonal matrices is called torus. Okay, this will geometrically form a torus, and all the longitudes will become conjugates of the torus. And these horizontal structures, which are two-dimensional sphere within the three-dimensional sphere, they will be the conjugacy classes of SU2. Yeah, every group has conjugacy classes, right? A group is a disjoint union of conjugacy classes. And the conjugacy classes of SU2, if you map them in a three-dimensional sphere, they will turn out to be latitudes. Okay, so this is what I want to explain today and next time. Any questions?
No, sir.
Participants, anybody more? If you have any query, then you can.
It's hard to catch at a time, sir, because if you,
Yeah, I am summarizing contents of 2 lectures.
yeah. Oh, okay.
Just to tell you what is coming. This one has to look at the whole picture also together.
Okay, sir.
Yeah. So each one will become some proposition or some theorem, what I have put in this single page.
Okay, that's fine, sir. Because otherwise, for catching this one is very difficult because you are saying many things as the single slide.
So slowly the whole picture will be revealed.
Okay, sir. Yeah.
Okay. All right. So let us now start proving the various parts. Okay. So first topic is so keep this big picture in mind. So we have the algebra of quaternions R4, consisting of A plus BI plus CJ plus DK, where A, B, C, D, they are real numbers. And inside R4, I have the algebra, the subalgebra. I mean, it is a subspace. It is not an algebra. It is a subspace of purely imaginary quaternions. AI plus BJ plus, B, I should say, BI plus CJ plus DK, where A, B, C, D belongs to R. This is the set of purely imaginary quaternions. Okay, this is linear span of these 3 vectors ijk, which are linearly independent, and therefore V as a vector space is isomorphic to R3. Okay, yeah. Now in complex numbers, if you take the complex numbers whose absolute value is 1, they form unit circle. Yeah, they form unit circle, and points on the unit circle, they can be parameterized like this: cosine theta plus I sine theta. These are complex numbers of absolute value 1. So, and this I, okay, I square equal to -1. So all complex numbers of unit length or unit absolute value, they can be written as linear combinations of 1 and I, and these scalars are cos theta, sin theta. It has unit length, so we can write it like this. We want to do same thing for unit quaternions. Yeah, can we represent unit quaternions in a similar way? The answer is yes. Okay, so we want to show that any unit quaternion So you remember, unit quaternions are corresponding to points on 3-dimensional sphere, right? So any unit quaternion, we will see that it can be written as cos theta plus u times sin theta, where u square is -1. So it's completely analogous to the field of complex numbers. Okay, but in the field of complex numbers, this I whose square is -1 is a unique complex number. And we'll see that this u, okay, this u can be chosen from the 2-dimensional sphere contained in V. See, V is 3-dimensional vector space, right? V is 3-dimensional vector space. Inside 3-dimensional vector space, I have 2-dimensional sphere. So the quaternions which are corresponding to points on the 2-dimensional sphere, we write them as u. All those will satisfy u square equal to -1. Okay, so I want to first explain this representation of unit quaternions. That is, quaternions which are corresponding to points on S3, and these are also representations of matrices in SU2. Okay, so we are, if I give you a quaternion, you can construct a unique matrix in SU2 and vice versa. Okay. All right. So now let us show that the imaginary quaternions do not form a ring. They just form a vector space. So suppose I take two imaginary quaternions, u equal to AI plus BJ plus CK, and V equal to XI plus YJ plus ZK. Okay. Now we can multiply them as we multiply quaternions. So u times V. Okay. What is u times V? It is AI plus BJ plus CK times XI plus YJ plus ZK. Okay. So if you multiply them, a times x goes with the I square is -1, b times y, b times y will go with j square. So it is ax plus by plus cz, but it will come with a negative sign. Yeah. Then if you multiply other quantities, you will see that it is equal to I times bz minus cy plus j times cx minus az plus k times ay minus bx. And if you stare it a little bit, you will see that this quantity, this is equal to negative of the inner product, dot product of u with v, and this other quantity, which is linear combination of I, j, k, is really the determinant of I, j, k, and then a, b, c, x, y, z. Just see, the coefficient of I will be bz minus cy, right? This is bz minus cy. Coefficient of z should be xc minus az. Coefficient of k should be this 2 by 2 determinant with ay minus bx. Okay, so this is the product of two imaginary quaternions is equal to their cross product minus their dot product. Right? This cross product is certainly inside V, the space of imaginary quaternions. But this U, this is giving a real part of this quaternion. Yeah. So if U and V are perpendicular, then and only then UV also belongs to it's a imaginary quaternion. So product of imaginary quaternion need not be imaginary quaternion. But if those two quaternions are perpendicular, okay, then and only then it is going to be in a imaginary quaternion, and it is going to be the cross product. Yeah. Okay. So now if I take U equal to V, then what happens? This cross product becomes 0 because U and V become parallel. The angle between them is 0 degrees. So cross product will become 0. And so this will be the left hand side is U square. The right hand side is minus of square of length of U. And that is equal to minus 1. So U square equal to minus 1. Okay. So if I take this unit quaternion which is imaginary, a purely imaginary unit quaternion, and then it will say that U square is minus 1. Yeah. Okay. So let me write, if U belongs to V, which is the set of purely imaginary quaternions, and the length of U is 1. Yeah. V is three-dimensional space. Length of U equal to 1 means it is on the unit sphere. This unit sphere is in three-dimensional space. My three-dimensional space is V, which is the set of imaginary quaternions. They form a three-dimensional space. And in this three-dimensional space, there is a two-dimensional sphere. And if I take a vector which is this on this two-dimensional sphere, its length is 1, and this formula says that U square is minus 1. So it says, therefore x square plus 1 equal to 0 has infinitely many solutions. In fact, S2 is the set of all solutions. These are all the quaternions of unit length Yeah. So this doesn't happen in a field. If you take equation over a field of degree n, it has at most n solutions. But now we are working in a non-commutative field. In a non-commutative field, you just see that U square equal to minus 1 has as many solutions as points on the unit sphere, two-dimensional sphere in R3. Is that point clear?
Yes, sir.
Yeah. You see, that is the difference between the commutative world and the non-commutative world. When you have a field, the usual field, then polynomial of degree n has at most n solutions. But now we are working in a skew field. The quaternions form a skew field. Multiplication is not commutative, but all other axioms of a field are satisfied. And in this skew field, we took the space of purely imaginary quaternions, and inside that three-dimensional space of purely imaginary quaternion, we have two-dimensional sphere. These are purely imaginary quaternions of unit length, and these all satisfy the equation x square plus 1 equal to 0. Okay, so this quantity U is analog of I square. So I square is also minus 1, right? I square, if I is that complex number, I square is minus 1. But when you look at the same equation inside the space of purely imaginary quaternions, then it has infinitely many solutions. Now, if I take any quaternion, right? If I take any quaternion of unit length, if Q equal to A plus BI plus CJ plus DK has unit length, yeah, that corresponds to a point on 3-dimensional sphere, and then A square plus B square plus C square plus D square is 1. So I write this as cos square theta, and I write this as sine square theta. Okay, then I can write Q equal to cos theta plus 1 over B square plus C square plus D square, okay, times, just a minute. Yeah, B, okay. So I write B, yeah. So sine theta is square root of this, okay, times, yeah, times BI plus CJ plus DK. Okay, so this is equal to cos theta plus sine theta times BI plus CJ plus DK over square root of B square plus C square plus D square. So this quaternion has unit length, and it is a purely imaginary quaternion. So this is, I am writing as U. So this is equal to cos theta plus U sine theta, and U square equal to -1. So every quaternion of unit length, I can write it as cos theta plus U sine theta, where U is a unit quaternion. Okay, it's a purely imaginary unit quaternion. Yeah, any questions so far? All right. So now you see, we have familiarity with complex numbers, and we want to use our intuition about complex numbers to prove results about quaternions. Yeah. So not everything goes through, but there are some analogs. So in the field of complex numbers, yeah, in the field of complex numbers, if I take a complex number of absolute value 1, it can be written as e to the power I theta. Yeah. So that corresponds to a point on S1. S1 is the unit circle, and every point I can represent it by e to the power I theta, and as a vector it is cos theta sine theta. But now if you take this complex number of unit length, unit absolute value, and use this to define a multiplication map. Yeah. So if this is Z, then Z e to the power I theta. Okay, that will be a complex number. Yeah, suppose my absolute value of Z is also 1. Then if I multiply by e to the power I theta, then I get this complex number where this angle is this. Because, yeah, that is clear by polar representation of complex numbers. So yes, in this space of complex numbers, C to C, if I take Z and multiply this by e to the power I theta, this is a rotation of the plane. Yeah. So we want to see whether we can do a similar thing with quaternions. Can we produce rotations of space using quaternions? Okay, and the answer is yes. The answer is very interesting. It is yes. Yeah. So we used a complex number of absolute value 1. Yeah. So suppose we pick up a quaternion of unit length. Suppose T is a quaternion of unit length. Yeah, this is a quaternion unit length. So we try to mimic the same construction. Now we will define a map phi t from quaternion to quaternions. This is a vector space. H is a vector space also. So I'm thinking now H as a vector space and take a vector in H. A vector in H is A plus BI plus CJ plus DK. Okay. And I multiply this vector with T on the right hand side. That is my phi T. Okay. All right. Claim phi T. Okay. Phi T is an orthogonal transformation. Orthogonal linear transformation. Okay, let us see that phi t is linear. So suppose I take q1 plus q2. This is equal to q1 plus q2 times t, and that is equal to q1t plus q2t. Multiplication is distributive among quaternions. Quaternions form a ring and it satisfies two distributive laws. Okay, so and then if I multiply by a real number, a quaternion, this x is a real number. Okay, then this is equal to xa plus xbi plus xcj plus xdk times t, and that is same as x times qt. So x times phi tq. So these things show that phi t is a linear transformation. Now, what should I prove to show that phi t is an orthogonal transformation? Can anybody answer?
Yes, participant.
Yeah. Phi t preserve angle as well as phi t preserve length.
Yeah, length should be preserved.
Yeah.
Yeah. So to show that phi t is orthogonal, phi t is orthogonal if and only if the length of phi tq is equal to length of q. Yeah. This is if and only if length of tq is same as length of q. But show, very easy exercise. If I take two quaternions and take their length of the product, it is product of the lengths. Okay, so therefore, length of tq is length of t times length of q, but length of t is 1, so this is length of q. And therefore, phi t is an orthogonal linear transformation. Okay, similarly, q mapping to tq is also an orthogonal linear transformation. Yeah, this is also a linear transformation. And composition of two orthogonal linear transformation is also a linear transformation. So this says that if I pick a unit vector, a unit quaternion t, then gamma t is the map which sends q to t inverse qt. Yeah, this is a conjugate of Q. This is orthogonal linear map of H. Yeah, H is 4-dimensional space. And in this 4-dimensional space, I'm picking a unit vector, a unit quaternion T, and taking this conjugation action on all the quaternions. Conjugation action by unit quaternion, and this is a orthogonal linear transformation. Now, orthogonal linear transformations, this is 4-dimensional space. You see, this is 4-dimensional space. So let us show that this orthogonal linear transformation, if I restrict it to the 3-dimensional space of imaginary quaternions, it is going to be a rotation. I have not defined what is meaning of rotation in 4-dimensional space. I have defined meaning of rotation in 3-dimensional space. H is R4. Inside R4, I have the space of imaginary quaternions, which is isomorphic to R3. Okay. Now I am picking T belonging to S3. S3 is the space of unit quaternions. And I am using this T to define a map from V to V, which is orthogonal linear transformation. It sends Q to T inverse QT. Let me give this name, gamma T of Q. Yeah. Are you with me?
Yes, sir.
Yeah.
Yes, sir.
So just like complex numbers of absolute value 1, they can be used to define rotations of 2-dimensional space. I am trying to construct rotation of 3-dimensional space using quaternions. But I am using quaternions of unit length for the obvious reason that rotations have to be orthogonal transformations. They must preserve length of vectors. And therefore, I must choose unit quaternion. Unit quaternion are in one-to-one correspondence with the points on 3-dimensional sphere. So I pick any point on this 3-dimensional sphere, take this, and so think of this as a quaternion, and then take an imaginary quaternion and map it to T inverse QT. That is a conjugate of this quaternion, imaginary quaternion. You can also think of Q as a matrix, a 2x2 matrix. After all, imaginary quaternion looks like Bi plus Cj plus Dk. And I showed you last time that this IJK are identified as 2x2 matrices, which are orthogonal of determinant 1. Okay, so you can think of this imaginary quaternion like a matrix, and then T inverse QT is a matrix, and that is a conjugate of this matrix. So I am doing conjugation action on SU2. Okay, taking quaternions of unit length. But this is a linear transformation from the space of imaginary quaternions. Okay, I want to show that this is a rotation. Theorem. This is the theorem for today. Yeah. So let T be equal to cos theta plus U sine theta be a unit quaternion where U square equal to -1. So I showed you how a unit quaternion can be written like this. So take a unit quaternion which can be written like this, and this vector U is a vector in a 2-dimensional sphere. Okay, it's a vector in 2-dimensional sphere. A vector in 2-dimensional sphere has unit length, and this 2-dimensional sphere lives inside the space of imaginary quaternions. This U is a purely imaginary quaternion of unit length, so it corresponds to a point on the 2-dimensional sphere. Okay, a point on the two-dimensional sphere. So take the line passing through this point and the origin, that is going to give me an axis of rotation. Okay, so pick this unit quaternion where U is a purely imaginary unit quaternion. And then this gives rise to a map gamma T from the space of purely imaginary quaternions. And this map sends Q to T inverse QT. So it's a conjugation action on this three-dimensional subspace of unit quaternions. Okay, then this gamma T is a rotation. It is a rotation along the axis, which is linear span of this vector U, and angle of rotation is 2 theta. Okay, so this gives a very clear algorithm to write a formula for rotation along an axis U in three-dimensional space, and the angle of rotation is 2 theta. And this rotation is a map from V to V, and it is a conjugation action. Yeah. So you can prescribe your axis of rotation. This is my axis of rotation. Okay. This is the axis of rotation. So axis of rotation can be thought of as a vector on two-dimensional sphere in three-dimensional space. And 2 theta is the angle of rotation. Then construct this quaternion, T equal to cos theta plus U sin theta. Okay. So any vector on S2 can corresponds to a imaginary quaternion of unit length, and then construct this quaternion, and using this quaternion define this conjugation map, that is a orthogonal linear transformation, which we already seen, but this theorem is saying that it is actually a rotation. And the axis of rotation is the linear span of U, the line which is spanned by U, and the angle of rotation is 2 theta. So we need to prove that a line which is spanned by U is the axis of this rotation, and the angle of rotation is 2 theta. These are the two facts we have to prove. Okay, is this clear what we want to show in this theorem? Any
Yes, sir,
doubts?
yes.
Any doubts in the statement of the theorem? This theorem is going to provide us a connection between SU2 and SO3. You see, I am bringing things from SU2. SU2 is same as the three-dimensional sphere, and this T is taken from the three-dimensional sphere. Okay, so I'm taking data from SU2 and I'm producing something in SO3. Okay, this will lead to a very beautiful connection between SO3 and SU2. And the basis is this theorem, how to produce rotation maps using quaternions. Okay, yeah, so let us start proving this. Okay, so we want to show, first thing we want to show is that the line which is spanned by U is the axis of rotation. And this is same as proving that gamma T of U, what should be this? If you want to prove that the axis is the line spanned by U, what should you prove about gamma TU?
The same.
T inverse QT.
No, but to show that this is along the axis of rotation, what is the action of gamma T? What should be the action of gamma T on the axis of rotation? Should be u only, right?
Yeah, the same. Yeah, on the line.
Okay, so let us prove that. Let us prove that. So T inverse ut, okay, T is equal to cos theta plus u sin theta. And then u cos theta plus u sin theta. Inverse of a unit quaternion. How do we find inverse of a quaternion, unit quaternion? It's just the conjugate. So this is cos theta minus u sin theta. U is purely imaginary quaternion. And so you just replace purely imaginary part by minus, then you get its conjugate, and conjugate is the inverse of a unit quaternion. So this times u cos theta plus u sin theta. Now just multiply. This is equal to u cos theta minus u square, which is plus 1 plus sin theta, then cos theta plus u sin theta. And this is what? This is u cos square theta plus sin square theta plus cos theta sin theta plus u square cos theta sin theta. What is this? What is this? Anybody?
You.
You, sir. Last two
Yeah.
terms cancel.
Yeah.
This
you.
1
Last
and
two
u
terms.
square is minus 1. So this is u.
Yeah.
So T inverse ut is equal to u. And you see, gamma t is a linear transformation. Gamma t is linear map, and therefore gamma t of alpha u will be alpha u. So this entire line along u is fixed. This is mapped to itself under the action of gamma t. So this is the axis. This is the axis of possible rotation, but we have not proved that gamma t is a rotation. Yeah, but gamma t of q is equal to t inverse qt, and the length of t is 1. This says that gamma t is orthogonal linear map. If you want to show that an orthogonal linear map is a rotation, what can you do? What do you have to do? I have found the axis of rotation. Yeah, and gamma t is our linear map. To show it is a rotation, I must restrict it to the plane of rotation. Yeah, and then gamma t should map vectors in this plane of rotation to itself. Yeah, gamma t, which is a map from V to V, space of imaginary quaternions, and u perv lives inside, it's a plane inside this three-dimensional space, and gamma t, I want to show gamma t will map vectors which are perpendicular to u to vectors which are perpendicular to u. Yeah, so if V is perpendicular to u, then gamma t of V, okay, gamma t of V. I want to show that this is also perpendicular to u.
Yes, sir.
This should also be 0, but this is equal to T inverse V T U. Yeah. Now you see u and gamma TV, they are both imaginary quaternions. They are both imaginary quaternions. Because gamma t is a map from V to V. V is the space of imaginary quaternions. So gamma t, V and U both are imaginary quaternions. And when I want to test whether gamma t V is also perpendicular to U, yeah, it is also perpendicular to U. Yeah, this should be true for any orthogonal map, right? Should be true for any orthogonal map because this U is same as gamma t of U because U is fixed. And orthogonal map preserves dot product. This is same as VU. And this is 0. This is U. And therefore, gamma t V is also in the same plane. So gamma t is a map from V to V, but it is also a map from this perpendicular to plane to itself. Okay. So this gamma t is an orthogonal transformation of a two-dimensional subspace of V to itself. And I will show that this is a rotation. Yeah. So gamma t as a map from this plane, call this plane as W, from W to W is a rotation. All right. So W is the perpendicular space to U. So I take some unit vector, take a unit vector in this plane. Okay. Take this unit vector in this plane. So here is my U and here is V. And then I take U cross V. Okay. U cross V. This is the direction of U cross V. So U cross V, norm of U cross V, what will be this norm? This norm of U, norm of V,
1.
times 1, but this is 1. So U, V, and let's call W to be the cross product. This is orthonormal basis of V. Yeah, that is an orthonormal basis of V. So the plane W is spanned by V and this V and U cross V. Their linear span is this plane which is perpendicular to U. Okay. Yeah. So now we want to understand that this gamma t from W to W is a orthogonal transformation and it is a rotation. Okay. So to do that, we have to make one calculation, and I will leave this as a reading exercise. So reading exercise. Okay, this is my W. Reading exercise. So these are quaternions. You see, U, V, W are unit quaternions. Okay, and this U was purely imaginary unit quaternion. Okay, and V is also a purely imaginary unit quaternion because I picked V from the perpendicular space of U inside the big space V. So U and V and U cross V, they are all unit quaternions. Okay, now check that UV is W, VW is U, and WU is V. Okay, check this. Yeah. So the U, V, W are behaving like I, J, K, right? If this is I, this is J, this is K. Okay, They are analogs of ijk. And this is understood because this is a basis of the purely imaginary, the space of purely imaginary quaternions. But check using multiplication of quaternions that this is true. Okay. Now look at T inverse Vt. Okay. Look at T inverse Vt. So T, what is T? T is cos theta plus u sin theta. It's a unit quaternion and I wrote it like this. So for ease of computation, I will write this as C plus SU. So this is C plus SU inverse, then V C plus SU. This is C minus SU, V C plus SU. And this is equal to, you can check, this is CV minus SUV C plus SU, and this is equal to C square V plus CSU minus SUVC plus S square UVU. Okay, so, but now you see UV is equal to W. This is W. And this is UVU, so that is WU. WU is V. So this is V. So I have C square V and I have S square V. So this is C square plus S square V. And this CSU and so this is, just a minute. This is CSW. Something is wrong. CSUV. UV is W, you see. I multiplied CV, the CV with SU. So that is CSVU. CSVU. So VU, what was VU?
The second term is C. Second term is C.
V, yeah, V is missing, yes.
Yeah. So this should be minus 2CSW. UV is W. Okay. So this is equal to V. This is C square. Sorry, this is C square minus. This is C square minus S square. Yeah, C square minus S square. So this is equal to cos 2 theta V minus sine 2 theta W. So that is my gamma T of V. You see, gamma T is acting on the plane which is spanned by V and W. That is the plane, and I'm looking at this action of gamma T. Gamma T is also an orthogonal transformation of the plane which is spanned by V and W. Okay, and I have shown that gamma T is mapping this vector V into a linear combination of V and W. And the coefficients are cos 2 theta and sine 2 theta. Okay, same calculation you please do on W and show that this is equal to V sine 2 theta plus W cos 2 theta. So therefore the matrix of gamma T with respect to the basis V and W, okay, that is equal to V is mapping to this vector, so it is cos 2 theta minus sine 2 theta, and W is mapping to this vector, so it is sine 2 theta cos 2 theta. So therefore, this matrix M is orthogonal matrix. That was expected. And what is the determinant of M?
1.
1, 1.
1. 2 by 2 orthogonal matrix of determinant 1. What does it represent?
Rotation.
Rotation. And the angle is 2 theta, you see.
Mhm.
Angle is 2 theta. So angle of rotation is 2 theta. So you see, we have a recipe now. How to construct, this is a recipe, how to construct a rotation of angle 2 theta and axis u, where u is a unit vector. Yeah. So I am in 3-dimensional space, okay, and I want to construct a rotation where the axis of rotation is along this vector, and I can assume that u is a unit vector, okay, and I want the rotation is in this plane and the angle of rotation is theta, 2 theta. I just write the angle of rotation as 2 theta. So then what this theorem says, well, take your vector u, okay, this is some, it is in 3-dimensional space, so it is some xi plus yj plus zk. Now this ijk are the standard basis vectors of 3-dimensional space. You see, they are being interpreted as quaternions also, okay. So this unit vector I can write as xi plus yj plus zk, where ijk are the standard basis vector along x-axis, y-axis, z-axis, okay, and the angle of rotation is 2 theta. So what is this recipe saying? Well, from u, you make the following quaternion: cos theta plus u sin theta. Interpret the same vector as a quaternion. Okay. So the notation is very carefully chosen so that there is no confusion. So take this unit vector, interpret it as a quaternion, and then form this vector t equal to cos theta plus u sin theta, and then gamma t from the space of purely imaginary quaternion to purely imaginary quaternion is a rotation of R3, okay, with axis u and angle 2 theta. That's what this theorem is saying, okay. Yeah. So what have we done? What have we done? So S3, remember, S3 is isomorphic to SU2. So I pick a unit quaternion. A unit quaternion, selecting a unit quaternion is same as selecting a matrix in SU2. Because this unit quaternion will have 4 coordinates, A, B, C, D, and their sum of squares will be 1. And then I have a method to associate with T a matrix in SU2. But SU2 and S3 are isomorphic. Once I select this T, then I pass to the rotation gamma T from V to V. That is a rotation. So this gamma T, because it is a rotation, its matrix is in SO3. Okay. So this gives us a map from SU2 to SO3. The map is T mapping to gamma T. This map phi is a group homomorphism. Why? Because suppose T1 and T2 are in S3, then gamma T1 T2 Q equal to T1 T2 inverse Q, T1, T2, but that is same as T2 inverse, T1 inverse Q, T1, T2, and this is gamma T2, gamma T1 of Q, and therefore gamma of T1, T2 is equal to gamma T2, T1. Okay. Yeah, so the order has reversed. The order has reversed. Right. Okay, this can be fixed. I'll fix this thing. But this is a group homomorphism, and this last theorem says if I am given a rotation, that means a matrix in SO3, yeah, then this comes from gamma T. I can construct a T so that gamma T is this rotation. So this is onto map. Okay, but it is not an isomorphism. It has a kernel. The kernel of phi is set of all T so that gamma T is identity. But gamma T equal to identity if and only if T inverse QT equal to Q for all Q in V. But this means T inverse QT, this is equal to QT is equal to TQ for all Q in V. So in particular, QT equal to TQ for all Q in S3. Just a minute. Yeah. In S3 also. Why? Okay, this needs a little argument, but let me complete this. So this says that T belongs to the center of S3, but the center of S3 is just I1 and -1. Or if you want to think of this in the SU2 group, it is identity and minus identity. This will be done in the tutorial. The center of SU2 is I and -I. Okay, so the kernel of SU2 and the kernel of phi is equal to I and -I, and that means that SU2 mod I and -I is SO3. Okay, there are a few points here, but my time is finished. You can read the lecture notes for some missing arguments, but this is what I wanted to prove today, that the space of rotations, the group of rotations of three-dimensional space is a quotient of the group SU2. And this isomorphism we have derived using quaternions. So they were, you see, SU2 consists of 2 by 2 matrices, right? Unitary matrices whose determinant is 1. Computing with matrices is a little bit cumbersome. So what we have brought in quaternions to do these computations. So we didn't write any matrix. No, when we are doing computation with quaternions, we are just using the rules of computation. Ij is k, j, k is I, etc. Okay, we just use rules of computation of quaternions, and we don't write any matrices. but the conclusions are about the group SU2, because SU2 is isomorphic to S3 and S3 is the space of unit quaternions. Okay. Yeah, so we will stop here and we will have tutorial, and then on Saturday, I will do the remaining portion about how the conjugacy classes in SU2 correspond to latitudes of this three-dimensional sphere, yeah, and how subgroups correspond to some subgroups correspond to longitudes of this three-dimensional sphere. Okay, so I will stop here.
Okay. Thank you so much, sir.
Yeah.
For nice lecture.
Thank you, sir.
Thank you, sir.
Yeah, we'll meet at 6 for tutorial.
Yes, sir.
Okay.
Okay.
Okay, participants. So we will meet again after 30 minutes. You have a break. Thank you.